Hey everybody, and welcome back for another installment in our VHDL design series. Today we're going to be talking about something that's really helpful in some cases inside VHDL design called subprograms. A subprogram basically, think in terms of another language like C, where you have function calls. So you can create functions in there. Sometimes other languages have things called procedures and such. So it's basically a way to organize your code into groupings inside VHDL. Now don't get too excited because functions and procedures, while beneficial and useful, do have quite a few limitations and should really not be used in more complex things. They're really mainly intended for simple, short bits of code that you repeatedly do inside your system. So if you find yourself doing something over and over again, you don't want to be rewriting the same code. You want to just consolidate that into a single routine, and then you can call it multiple times inside your code. If it's a really complex thing, then you would create a separate component with its own entity and architecture and reuse that in the design. So that's really the preferred way to do something that's more or less complex. So let's take a look at some differences in characteristics of subprograms and see when we can use them in our system. Basically, subprograms, like I said before, are very similar to functions and procedures that you might see in other high-level languages. Just like in a process, all subprograms are sequential in nature, so the statements are sequential. Also, you can use subprograms in just about any area. You can even embed them within each other. So you can have a function within, for instance, a procedure. You can have them inside processes. You can have them in the architecture concurrent area. So they can be used in a variety of different places. The one thing, and this is the kicker, the one thing that basically makes subprograms somewhat limited and also complex to use is the fact that variables that are created inside a subprogram are initialized every single time it's called. So in a process, we've used variables before as a means for temporarily storing information. So we can create a counter and create a count variable inside, and then when we leave it and come back to the process later, it retains the value that was in that variable. That is not the case with functions and procedures. So you have to be really careful about how you use a function and procedure, and you are limited in the ways you can. So the biggest caveat here, the biggest thing to take away is this fact here. Oops, let's use a bigger pen to highlight that. Is that variables are created and initialized each time the program is called. So it limits you in what you can do. Now we're going to see some great examples of the two different types. Functions and procedures, and they're useful in different places and in different ways. What you use really depends on what you're trying to do. So let's take a look first at what functions look like. Now we've already gone through code and used functions in our design. In fact, we've been using a function called rising edge over and over and over again as a way to detect whether there is a rising edge on a clock signal. So that's something that we've made great use of and found incredibly beneficial. Basically, functions are things that have to be used as part of an expression. They can be used as part of a signal assignment. They can be used within code, like I said, within a process, within another program or a subprogram like a procedure. But they're always part of some expression because they always have a return value and they have input arguments. So here are some key characteristics that we want to remember. They accept one or more. Oops, got the wrong pin there. Let's go back to this one. Basically, they accept one or more inputs, so you can have as many inputs as you want. Now, obviously, you can get out of hand. You don't want 20 inputs into your function. That would make it something that you would probably want to consider using a component for. But functions, typically, the functions that I've used and created typically have 3 arguments or so, 2 or 3 arguments. And then they have a single return value, and that's another limiting factor of functions. Since they have a single return value, you can't have multiple signals coming out of a function. You can think of functions in terms of ways to convert from one thing to another, or ways to analyze something that you continually do, like the rising edge function. It returns, like we said before, returns a single value. It also has a type associated, which is its return type. So functions are typed, so they have a type associated with them, and that type represents what the return type is. And that's important because when you use a function in an expression, then that expression requires a value to evaluate the expression with, and that value needs a type. And so every function has a type associated with it. So it's say standard logic vector, Boolean, integer, whatever. Depends on what you've written. All the arguments inside the argument list of the function are going to be inputs. You don't have a choice. That's just what they are. Now, one of the things that you can do, which is interesting, is you can also use a keyword signal on one of those inputs, and it will inherit signal attributes. Now, this is important for our first function example, because if you remember, signals can have attributes, and we can use those attributes as ways to detect if things are happening of interest. And the rising edge example is just one such place where we would do that. You do not always need this signal in front of your thing, only if you're using aspects of the input that require you to look at signal attributes. Okay, so that's the only time you can do that. And here's a very important piece. Functions are only used for combinational logic. So not things that have storage or sequential logic, but basically combinational logic. And that's a pretty limiting factor for the use of functions. Let's take a look at this first example, and we're going to look at another one in a minute that's more complex. But this function here is the rising edge function. Now, as we've seen before, the rising edge function was declared as part of the standard logic library that we continually use, the 1164 IEEE library. That library has this function declared in it, and it almost looks identical to this one if you go look at the specification. Now, it is a little different in the sense that it uses more low-level types, okay, not the high-level standard logic, but it uses a lower-level type inside the declaration of the official library. But it looks pretty darn similar, and it checks for the same kind of things. Remember, when we're checking for a rising edge, we use the event attribute here to tell if the signal had an event associated with it, and then that's why this is being called. Then we have the current value of the signal, which would be a 1 in case of a rising edge because it's going from low to high. And then we also check another attribute called last value to see if it was 0. So if its previous value was 0, its current value is 1, and an event, and it represents an event change, then this is a rising edge. And so we can return a true for that. So if this is true, and that's true, and that's true based on Boolean logic, the whole expression is true, so it will return a value of true. And so this is a function that we've seen immense benefit from and use it continuously. Not only does it save us a lot of typing for these different parts of the return value, it also documents the code better, because when you read a function rising edge, you know exactly what you're checking for. But if you saw this expression as part of your if statement, then you might have to take pause and think about it. So I just like it for the self-documenting characteristics of it. And remember, in VHDL, a lot of times we get caught in a loop where we're thinking about efficiency, right? So we're used to programming in languages like C or Python, and we're looking at how to make it the most efficient possible code that we can. And so efficiency in VHDL is very different than efficiency in other high-level languages. Using a function in a high-level language can oftentimes have an impact on performance, because if that function is called within a loop, then that will chew up a lot of time as it sequentially processes the information in your program. In VHDL, however, that's completely not the case, because in VHDL, remember, all the processing is done prior to it being put on your design. The whole purpose of the code is to describe hardware that the system will then map to your resources. So you don't have to worry about code efficiency as far as looping structures and other things like that, because it just doesn't matter in the VHDL world. Now, it might impact your synthesis time and simulation time, but it was not going to affect the efficiency of your design. So let's take a look at another example function that I think will be very, very beneficial. And this is something that comes up quite a bit. And it is the need to convert a signal from an integer, say, into a BCD code. So in some of our previous projects, we've designed circuits that actually interface to 7-segment displays. So we have the 7-segment displays, and then we interface to those with BCD code. So we've seen in some previous videos where we talked about a 7-segment driver, and we can actually, highlight certain segments to create numbers like 7 in this case. And so that requires a BCD code. So this routine actually provides the conversion from a integer value to a standard logic vector value, where it's divided into 2 pieces. So it will have 8 bits, because this is called to BCD 8-bit, which basically means that we're converting the integer into an 8-bit BCD value, which means you can only get up to 99. So it's 0 to 99 would be the limit for the values in this case. And so we divide this into 2 pieces, obviously. So we have our first digit and then our second digit. Okay, so this could be like digit 0, and this could be like digit 1. And so each 4-bit chunk represents a number. So this could drive 2 7-segment displays on it. So for instance, if I were to put in the number, binary number, 16, or sorry, the decimal number 16, that translates into a binary value of 1 and 6. So it would be 0, 0, 0, 1, and then 0, 1, 1, 0, and that would be the output. Okay, so the routine takes in an integer value, 16, and then it spits out a ones digit and a tens digit for our display, and that will allow us to display directly to things. So this is a fairly common function for things that are driving 7 segments in a design. So it's found just about everywhere. And interestingly enough, it's incredibly easy to write in VHDL. All you have to do is think about what's happening with a number. So if you take 16, basically you're taking 10 plus 6. So you just need to isolate the tens position or the tens place. And you can do that by simply dividing 16 by 10. So if I take 16 divided by 10, that's going to give us 1.6. Now, because division in VHDL is integer division, if you have an integer on the left side, it's going to be an integer answer in your argument. And so basically this will result in the value of 1. And then when we do the modulus, which is basically the remainder, we take the value and divide by 10 and get the remainder, and that will end up being 6. And so that provides a fairly straightforward process for finding the tens digit and the ones digit for my value, for my number. So this is fantastic, right? So I've got this very easy to describe system, and then at the very end, all I do is return. So we use the keyword return, and we return the first 4 digits here, and then the second 4 digits here. Now notice I'm using some of the features of the numeric standard package, where we can use unsigned and some conversion functions. And that's very, very helpful for writing things in VHDL, especially in this particular case. So basically, I'm specifying this part and I'm concatenating it with that part, right? So this part here is that part there, and this part here is that part there. And so we're concatenating them together. We do this by taking the 10's value, converting it into a 4-bit unsigned, and then converting that back into a standard logic vector. So that was part of our standard numeric package capabilities, right? So that's all that's happening here. Now the big question you should be asking yourself is, now wait a minute. If I was writing this code, and I was writing this code in a processor, okay? So let's say I'm writing this code in a processor. Then that's going to be problematic, right? Why is that problematic? Well, because divide in a processor, especially an integer-based processor that doesn't have floating point, is going to be very time-consuming and difficult. And so I've got two divides here. I've got a modulus and then I've got a regular divide. So isn't that going to be inefficient? The answer is no, not at all. Why? Because that's not how this works. So the synthesis tool goes in, and the simulation tool goes in and looks at each function or process, analyzes it for all potential values, and comes up with basically a truth table of what are the inputs and what are the outputs, and then it shrinks that down into the most optimal hardware possible. So this is actually going to be optimized by the synthesizer as a piece of logic. Now, typically, I would say this will probably likely, since we have 8 bits here, and most of the LUTs, which we'll talk about later, that's the way they do logic. That's your number of inputs, or 6 inputs. Now, some FPGAs have less, but most are like 6. And so with that kind of, it'll take maybe 8 LUTs, plus or minus, to implement this thing, which is really efficient, right? So each one of the bits in the system would use 1 LUT, and then we're going to have very simple resources. Now, if you didn't follow that, don't worry about it. We're going to talk hardware later about exactly what's inside the FPGA, how it works, what is LUT is, and all that stuff. But just know that this code, while inefficient on a processor or a microcontroller, is actually not impacted by inefficiency at all in VHDL. All right, so that's the functions. We've seen 2 example functions. Let's take a look at the procedure. Now, procedures structurally are very different from functions. In fact, it looks a lot like, in a procedure, it kind of looks a lot like a process does. The arguments in the procedure include both the inputs and the outputs. And so if you kind of look here at the argument list, you'll notice that it kind of resembles a process, not a process. It kind of resembles a entity declaration, right? So the entity has inputs and outputs and modes and stuff, and so that's exactly what a procedure does. So each element of the argument list is going to have a mode. In this particular case, we have 3 inputs and then 1 in out. Yes, 1 in out. In out was used because we are actually analyzing the value. So since it's an out, if it were an output, we couldn't use it here, but in out makes it a lot easier to use, to analyze and look at that value as a feedback. So we have these modes are allowed. So in, out, and in, out are all allowed as part of this. And parameters have different types. So by default, a parameter is a constant, unless you specify that it's a signal or a variable. Now in this case, I'm specifying signals, and that's important because when you specify an argument as a signal, that means you can access the signal attributes. That's the only way to be able to do that. And so I specify that as a signal here so I can get to those attributes. And let's see how this thing functions. This is basically just a simple integer counter that counts from 0 to 99. on every enable. So there's an enable pulse in here that comes in, and if that's active, it tells the counter to count up, and if not, it won't count. So it needs the enable pulse to tell it to count. So it will only count on the count enable signal being active. This is a synchronous input. So we're clocking this very, very quickly, but we're going to control when it updates by using this control signal, right? So we're clocking this at every, say, 100 megahertz, 100 million times a second. But maybe I don't want the counter to count that fast. Maybe I want the counter to count every millisecond or every second. Then I can enable it every millisecond or every second so that it counts at that time and then doesn't count anymore until I enable it again. And this is getting back to that idea of control signals that control how things happen inside of a sequential system. So anyway, that's basically what we need to know there. Now, the other thing that I want to point out for the procedures is, yes, we can use wait statements in procedures, whereas you can't use wait statements in functions. So functions are very limited that way. But we can use wait statements inside procedures, although test benches might be a good place to have them and use them, but I would typically stay away from those in procedures. The other thing that I do want to point out is, let's see, yes, this is where this is basically comes in. We do a reset and we reset it to 0. We check for the rising edge, and then most everything is controlled by the enable active. So only when the enable is active does it go through and update the count. And it will update the count if the count is, between 0 and 98. Otherwise, it will set the count to 99. Now, there's a very important thing to recognize here, and this is one of the limitations of a procedure. You cannot declare a signal inside a procedure. Now, you'll notice before we had variables declared inside our function, and we can do the same for procedures. We could declare a variable as part of our procedure. But remember, variables inside these systems are cleared and reset every time you call it. So they don't hold or retain any values, which is different than a process. So in order to do something that has register-based storage, that stores a value, you have to have an external signal that's part of your signal list here. And that's why we have count here. So count is our external signal that we're controlling with our system. So that's pretty much it for the introduction of functions and procedures. You could get by with never using a single function or procedure in your design. They are very handy and useful for consolidating code that you use over and over again, such as the rising edge function. So they do have great benefit and value, but it's one of those things that has limited use, and so use them with caution and use them where they optimize your code or maybe improve the readability of your code. So functions and procedures can be beneficial, but only use them when you need them. If you got a complex thing, use another component. So create a new component and just embed it like we have in the past. All right, that's it for today. I hope you got something out of our discussion with the functions and procedures. Next time, we're going to show an example that uses functions and procedures all in one architecture so we can see a more complex interface of these different pieces. And we'll be using actually this very code here in our example. So stay tuned, look forward to that, and we'll see you next time. Thanks.